Now we also have some cryptography used to maintain our communications security. We have something like the public key cryptography. You may also hear this as PKI or asynchronous keys. Now, PKI is the public key infrastructure, and it is a huge infrastructure, or can be a huge infrastructure, on how we disseminate, revoke keys, these public and private keys. That's the asynchronous part. We have public keys, we have private keys, and they have an association. Now, this association is through a certificate authority, a CA, because they're going to be responsible for giving out these certificates that are associated with your public keys. Now, you can encrypt something with somebody's public key. Let's say we're in the same organization, and I want to send you some data, and I want you to be the only one that can read that, to see the message. So what I could do is encrypt that data with your public key. Now, since the public key and private key have that relationship, the only person that can unlock that package is the one that has the corresponding private key. And that should be you, because we don't want our private key being compromised. It's private for a reason. It only belongs to you. It's not public where everybody can see it, but it's private. So only you should be able to unlock that package. Now, we can also have symmetric key encryption. And we've seen this already, we just didn't call it that. We called it a pre-shared key. But that's symmetric encryption. Both sides have the exact same key. It's not like a public and private where they have an association, a relationship, but they're different. Pre-shared keys are identical. So I could encrypt something with a AES key and send it to you. But now somehow I need to get that key to you. So I could call you on the phone, I could send you an email, I could send it snail mail, an instant message, all of which could have risks associated with that, could have vulnerabilities built into that. So whatever's best, but any way you can, you need to get that pre-shared key to the other person so they can unlock the data. Now, a lot of the times what can happen is, because symmetric key encryption and decryption is faster than asymmetric. So if I have large amounts of data that I'm trying to encrypt and send to you, I will use a symmetric key and encrypt that data. And I will send you the data. But now I'm going to take that pre-shared key and encrypt that with your public key. So I'm going to use asymmetric encryption to encrypt the pre-shared key and send it to you. So now you should be the only one with your private key that can unlock the symmetric key that I've encrypted, so you can actually get the data, the original data that I sent. Now that might sound a little convoluted, but that's a pretty secure way of passing data. Because again, somehow I have to get you that key. How am I going to do that? Using asynchronous or asymmetric encryption is a very good way of doing that, the public and private keys. Instead of me sending you an email, which is not secure necessarily, sending you an instant message, which may not be secure. Snail mail could be secure, but somebody could steal it, may not get there, theft, it's very slow, right? Or I could just walk it over to you and whisper it in your ear, I guess. Different ways we could get that information over to you. And then we have digital signatures. I think in domain 1, I mentioned the word non-repudiation. Non-repudiation means you can't deny doing something. If I digitally sign something, I can't say, well, Billy, I didn't send that email. Well, it says right here that you digitally signed it, Dave. I see that. So you can't say you didn't send it. Because a digital signature is your signature using your private key. You're the only one that's supposed to have your private key. So in that hash of your private key, you digitally sign something, and that goes along with the data. It's very popular to digitally sign your emails when you send them. So not only does that give you non-repudiation, that yes, I did send it, it also lets the other end trust that email a little bit more. Instead of just saying, well, I don't know if that's a fake email or somebody's trying to, if that's a phishing attempt. If it's digitally signed, that should give you a sense of trust. We're like, oh, well, Billy signed that. That's a digital signature. We're probably good to go. Unless his private key got compromised somehow, I would feel pretty good about that. Now, those certificates that I mentioned just a second ago, we can have different ones when it comes to secured communications. We can have client SSL certificates. On the flip side of this, I should mention, I don't think I put this on the slides, but anywhere we have SSL, we can have TLS, which is an updated version of SSL if you want to look at it that way. So an SSL client certificate, that's used to identify clients to the servers through the SSL, the secure socket layer. Now we can have server SSL, which is just the flip of that. It's identifying servers to clients. So now the clients can trust the servers. And you can have both, by the way, which is a good idea. Why does a server just have to trust the client? If I'm talking to you, I want to be able to trust you as well. So that server could have an SSL certificate, which lets me feel a little bit more at ease, right? When you go to your bank website, they have server SSL certificates. You'll see HTTPS, I hope. If not, you might not want to do any online banking there. But they could be protecting themselves with these secure socket layer certificates. We have SMIME certificates. This is used for signing and encrypting our emails. Very good idea to use. Encrypt those emails before you send them on, especially if you're sending any proprietary or confidential or sensitive information, stuff that you don't really want to get out there. We have object signing certificates. These are used to identify signers of program code. So you're a developer, you create some application, you can use these object signing certificates. Scripts, you can sign scripts with these. And in any other signed files, this identifies the signers. So you know that program is legit because they have that certificate associated with that object. And then you can have certificate authority certificates. CA certificates is mainly how you'll see it. But this is used to identify the certificate authorities, the CAs. How do you know where that certificate came from? This is where we look. You say, well, okay, this came from this certificate authority, and you start looking at the names and the credentials. And if it's in a reputable company, you might feel okay about that. If it's some company you never heard of before, or it's a self-signed certificate and they're doing online banking, online shopping, you might want to take a step back. Because of course I can self-sign a certificate. I'm going to trust myself, but that doesn't necessarily mean all your customers are going to trust you. You want to get probably a third party to vouch for you, right? There's tons of companies out there that will, for a fee, you prove you are who you say you are, and they send you the information electronically, and then you will place that in there. Then you will have a CA certificate, so when somebody says, hey, where did you get your certificate? You click on it, and it's going to show the CA, so now they can see, oh, okay, well, you got it from that company. That's pretty good. That's all right. And they're going to feel better about you. We also have something called single sign-on, SSO. This is meant to help end users, and they love this. I like it. I think it's nice. But a user's identity is actually shared across multiple applications within your infrastructure. So let's say you log on to application A, and you put in your credentials, but now you need to bounce from application or web services to web services. So if you logged out, or let's just say you kept your browser open, and you went to another application, total different application. It may prompt you to log in again, but it's the same username and password. It's the same infrastructure. Everything's the same. Why do I have to do that? Because they have different authentication mechanisms in them. So they came up with SSO. You log in once, and those credentials pass from application to application, making your life as an end user a little smoother. So authenticate one time, and that authentication is going to follow you throughout that session, from app to app or application to application. Now, there are some pros. I think I've mentioned those, but there are some cons too. Pros could be easier to administrate. That means we only have to change things in one place. If you had half a dozen applications and you had authentication and credentials for each one of your employees, you would have to administrate 6 different authentication mechanisms for every employee. So if you only have to change something once in one place, that makes your administration a little bit easier. It could be easier for your users. That's what it's meant for, right? They sign in one place and they can just go wherever they need to go inside of the infrastructure. We could have timeouts and thresholds across all apps. Again, easier for our administration. So if you log in this app and then you bounce to this app, if you sit there long enough, your session will time out across all apps, not just this one, and you're still logged in here. You'll time you out throughout the whole infrastructure, and now you'll have to log on again. So like if you go to lunch and you forget to log out, it should have a timeout set in there, a threshold of how long you can sit idle. And then once it meets that threshold, then you're automatically going to be kicked out. And we see that all the time. I mean, that's common. If you're doing online shopping or banking or online reservations or anything, it'll be, you have been idle for so long, would you like to stay? And you have to click OK. And if you don't, it's going to say you will be automatically logged out in 2 minutes, 5 minutes, 10 minutes, something like that. The cons of single sign-on, the bad parts, could be hard to implement. All right, it is a little harder than having, say, separate authentication mechanisms because you have to make sure everything works together. It could be expensive. You're going to have some dedicated software, perhaps. You may have to hire consultants or trainers if you don't have the technical skills to implement single sign-on. Could have a single point of failure as well. If I know a corporation uses single sign-on, I may try to DOS that particular service, so now you can't sign on anywhere, right? None of your applications are going to work because I'm trying so hard to attack that one particular system. Another con that I don't have listed there is if you lock yourself out, right? Sometimes we have thresholds of, you can only get your password wrong 3 times before it's disabled for 15 minutes. Or you have to call the help desk to get it re-enabled, or 5 times or whatever. So if I know that as an attacker, I may purposely try to guess your password wrong 5 times, and now I've just locked you out of the system, not just that one application, but for the whole infrastructure. So I just gave you an extended coffee break until it comes unlocked, or you call the help desk and say, I don't know what happened, I got locked out, and they'll reset your password. So the risks, again, single point of failure. All our credentials are in one location. Not the best idea, but on the flip side, it is the best idea because that's the easier to administrate part of it, right? I have one location where I need to change information. So again, this is the risk analysis we talked about. Is single sign-on worth the risk for easier administration? And then we also have a single point of access. Talked about that just a second ago, where I could DDoS that server and maybe cause some authentication issues. Now, coming up, we're going to continue on with Domain 4 and start talking about secure network components.